It is close to midnight when the emergency is called. An F-15 has just crashed in the Libyan desert, and its pilot is running for his life. Every passing second gets him further from being a survivor to being a geopolitical bargaining chip. The Arab Spring arrived in Libya in February 2011. What started as small sprouts of localized protest soon erupted into a violent civil war. The population was finally rising against the 42-year rule of Gaddafi, but the dictator's counteroffensive was brutal, with radio warnings echoing across the Libyan desert.
We are coming tonight. We will find you in your closets. We will show you no mercy and no pity.
Gaddafi unleashed the country's advanced fighter jets on its own people, and NATO drew a red line there, moving to impose a no-fly zone over the country with the combined air force of NATO. Amidst the chaos, the American pilot crash-landed behind enemy lines after a mechanical failure. His life now depends on this, the V-22 Osprey. For 30 years, this machine has been plagued by accidents and criticized as a technological Frankenstein, too complex to fly, a controversial hybrid of a plane and helicopter, but tonight only it could be the hero. Slowly unfurling its massive composite blades, the rings rotate 90 degrees and lock into place. Twin halos appear overhead as its blades thrash the air into submission. The V-22 now has to make its most difficult transformation. This aircraft has to operate in two modes, vertical and horizontal flight. Two completely different flight modes using the very same controls. This is the thrust control lever. It controls both the collective pitch in vertical flight, allowing the V-22 to control altitude in hover, but in forward flight it controls speed by controlling the engine's thrust, and altitude is controlled by the elevator, which is controlled by the stick. A fly-by-wire system was the only option to allow the control logic to flip like this, and things get even more complicated in the transition. With a turn of this wheel, the pilot effortlessly controls the nacelles, tipping them forward, trading vertical rotor wash for forward thrust. As this transition happens, the V-22 is neither helicopter or plane, and the computer has to gradually blend both control logics together until the transition is complete. But once complete, the V-22 is capable of flying nearly twice the speed of a Black Hawk helicopter. The V-22 is now flying low to the water to avoid ground radar detection on the coast. It is sprinting at 500 kilometers per hour, reaching the shoreline in less than 30 minutes. The pilots expected the cover of darkness, but they are met with a well-lit, populated sprawl, where they could be exposed to thousands of eyes. Forced to improvise, they thread the needle, aiming for the single darkest patch in a sea of city lights. Meanwhile, the situation on the ground is becoming desperate. Enemy vehicles have nearly cornered the pilot, and he is forced to call in a danger-close bombing run from US Harrier jump jets, dropping 500-pound laser-guided bombs, obliterating the trucks and forcing the pursuers to retreat in chaos. The explosions buy the crucial seconds needed for the extraction. It would have taken a standard rescue team hours to fly the 300 kilometers, but the V-22 arrived in just 41 minutes. As they approached the landing zone, the pilot rolled that dial back, redirecting the V-22's thrust at the ground, taking the V-22 from 500 kilometers per hour to a standstill. Opening its rear ramp amid a chaotic man-made sandstorm, the pilot sprints in from the shadows. A simple thumbs up, and in less than 90 seconds, the transformer raises its wheels off the ground, vanishing back into the clouds. For all its controversy, the V-22 is a miraculous piece of engineering. The V-22, just like any other aircraft, is a tool. It's not the most efficient helicopter, and it's not the best plane. But this rescue mission was exactly what it was designed for. This is the insane engineering of the V-22 Osprey. The development of the V-22 Osprey began in the early 1950s with the XV-3, a clunky aircraft with a piston-powered engine installed in the fuselage behind the pilot, with a 2-speed transmission allowing the rotors to operate at 2 speeds for hover and cruise. The rotors were mechanically linked to the engine through the wings, with the entire rotor assembly rotating through gaps in the fairings. This was the very first tiltrotor aircraft to transition from vertical to horizontal flight, and to honor its achievements, we've designed this t-shirt, screen printed on a 100% cotton shirt and designed to last. It's available to pre-order for the next 2 weeks with this link. The XV3 worked fine in helicopter mode, but these linkages and pylons lacked the stiffness needed to stabilize the intense vibrations and forces of transition to an entirely different mode of flight. These whirling vibrations through the skinny pylons got so intense that it knocked out test pilot Dick Stansbury, severely injuring the man and damaging the first prototype beyond repair. But Bell did not give up on the vision. The XV-15 was the next step to turn a prototype into a complete tilt rotor. Unlike the XV-3, the XV-15 moved the propulsion out to the fuselage and onto the wingtips. On the XV-3, the driveshafts and gearboxes had to transmit all of the engine's power out to the wingtips for the entire flight. That required heavy, robust driveshafts designed for long flights at high stress. But the XV-15 placed its engines on the wingtips. With the power from the engine being so much closer to the rotor, the pylons could be bolstered with a full nacelle that provided a lot of extra stiffness. But this created a new problem: how to synchronize the engines. The XV-15 developed an engine synchronization system that would carry on through to the V-22, a cross-shaft through the wings to keep the rotors in sync. The only time they would need to carry a large torque would be if one engine failed, where an automatic clutch disconnects the failed engine, letting the other engine drive both rotors through the cross-shaft for a single engine landing. With the smaller load, the shafts and connections could be a lot lighter. Up to the late 70s, these aircraft were mostly proof of concepts, but everything changed with one failed mission. Operation Eagle Claw was a US rescue attempt in April 1980 to free 52 American hostages in Tehran. The plan relied on 8 Navy RH-53D helicopters flying inland to a remote desert refueling site, Desert 1, and meeting 2 C-130s before continuing on to the city. Dust storms and mechanical failures cut the helicopter force from 8 to 5, below the minimum to continue, forcing commanders to abort the mission. Operation Eagle Claw highlighted a blunt limitation. Conventional helicopters could land anywhere, but they couldn't reach deep targets quickly without high-risk refueling stops. So, in 1981, the Pentagon responded by approving a program to design a transport aircraft capable of vertical takeoff and airplane-like cruise, setting the stage for the XV-15's 7-year-long evolution into the V-22 Osprey. The core concept of the Osprey depends on one mechanism, the conversion actuator responsible for the tilt that gives the Osprey its tilt rotor status. Even though the V-22 can fly with the nacelles at any incremental angle, in practice, to avoid complex aerodynamics, pilots use one of 3 modes: helicopter mode with the nacelles around 90 degrees, airplane mode with the nacelles locked at 0 degrees, and short takeoff and landing mode typically set around 60 degrees. The actual tilting mechanism has to handle a lot of forces that vary drastically depending on the flight regime. When the nacelle is in helicopter mode, the engine and rotor sit in front of the pivot, so gravity wants to roll the nacelle forward, compressing the actuator. But as the nacelle tilts down and the Osprey picks up speed, drag wants to push it back into the vertical position. That compression force decreases until around 80 degrees. As it rotates further, the load flips into tension. But once you get past the 45-degree point, the balance shifts again and the nacelle starts pushing the actuator down, putting it back into compression as it drives all the way down to the 0-degree downstop. Now the actuator's job is to keep the nacelle locked in place. With these changing loads, a gear drive would shove huge torque through small teeth that would wear and crack. A screw drive spreads that load through a larger contact area, but there is one problem with using a large, singular screw. The prop rotors reach well below the fuselage of the aircraft in horizontal flight. This means the V-22 cannot land like a traditional plane. If one of those screws jammed in horizontal flight, the V-22 would have no safe way to land. So, instead of having one large screw, the V-22 uses a double telescoping screw that saves space and provides jam redundancy. The size of these prop rotors are a great physical representation of the compromises that the V-22 had to make. They need to be both helicopter rotor and airplane propeller, and this blend of functions is what gives them their unique shape, sitting between the 4-meter diameter of a military transport propeller like the C-130s and the gigantic rotors of the Sea Stallion helicopter. The dual use also demanded a unique twist in the blade profile. Helicopter blades are twisted to adapt to faster flowing air at the tip of the blade, which would result in a disproportionate amount of drag here compared to the slower moving route. So the blade twists, usually around 8 to 14 degrees, to lower the angle of attack of the blade at the tip and balance lift. The V-22, however, has a massive twist angle of 47 degrees, an aggressive degree of twist driven by the prop rotor's need to adapt to high-speed horizontal flight. These are small helicopter blades, but absolutely massive propellers. In high-speed forward flight, the velocity of oncoming air adds to the high-speed rotation of the blades, with the airflow at the tips flirting at the boundary of supersonic speeds. The high degree of twist ensures the prop rotor can produce lift efficiently across its full length, despite the huge variation of airflow speeds it encounters. These tip airflow velocities limit how big a propeller can get, and that's a problem because the massive propeller is still a small rotor, and that really hurts the V-22's hover efficiency. Hover efficiency is measured by disk loading, the ratio of an aircraft's weight to the rotor's circular area. A rotor works by pushing air downward to generate upward lift. A helicopter like the Black Hawk has a disk loading of around 50 kilograms per square meter of its rotor area. The V-22 is closer to 150 kilograms per square meter. That means it needs to push air down much faster to fly. The V-22's downwash can reach velocities of up to 150 kilometers per hour. That's not just inefficient, that's stronger than hurricane force winds, which can make ground crew operations a little difficult. Powering the engine are two Rolls-Royce turboshaft engines mounted right on the wing tips of the aircraft, to prevent the whirling flutter-induced oscillations that knocked out the test pilot of the XV-3 prototype. The engineers of the V-22 needed light and strong materials to stiffen up the structure, and the V-22 benefited massively from a decade of composite material development for aircraft, like the F-14's first of its kind boron-coated tungsten fiber epoxy composite tailoron. Composites are everywhere in the V-22. 2,700 kilograms of the aircraft's total 6,000 kilogram structural weight is taken up by carbon epoxy composites. The wing structure got a stiffer carbon composite than the fuselage or tail, helping it deal with the huge variation of loads it was expected to hold and prevent them vibrating the entire aircraft out of the air. This is fairly standard composite manufacturing now, but back then it was worthy of NASA reports on state-of-the-art manufacturing. I wasn't lying when I said composites are everywhere in this. But on this long list of achievements, the prop rotors and their multiple parts stand out the most. Take the yoke, a part with a fairly simple geometry, an attachment point for the central driveshaft and 3 more for the gigantic folding blades. But it is constantly being battered by cyclical forces. Picking the wrong material could have it humming like a tuning fork before it cracks and fails. Titanium was tested in the XV-15, but it fatigued and cracked too quickly, forcing the engineers to rely on heavier, sturdier stainless steel. By the time the V-22 came around, they had figured out how to make it out of a much lighter S2 fiberglass composite, a glass fiber made from magnesia alumina silicate. Although not as strong as the carbon fiber blades it was securing, this material played a very important role with a unique property: its lower mechanical impedance. It's fantastic at absorbing, flexing, and transferring force without vibrating, which is why it's used in golf clubs and was recently used in the US Olympic team's pole vaults. They added layer after layer of this composite to build up this part to be strong enough to hold the enormous weight of the blades as they swung around and tried to rip free of their restraints, while also dampening a constant onslaught of vibrations that would crack another material. A problem they actually encountered further up the blade with the carbon composite part. The blade was made from stiffer, stronger carbon composites, but it also needed to fold over itself during the stowing process. During the development of these hinges, the grips kept delaminating and failing, eventually requiring the addition of a preloaded clamp ring to each end of the centrifugal force fitting to react the transverse load. Composites are not tough materials either. High-speed debris strikes can easily shatter them, so they need to be armoured. The leading edge is protected with a hot-formed titanium strip over the first 3/4 of the blade. Titanium gives a tough, erosion-resistant surface without adding too much weight. Further out, the impacts get much harsher, so further out they bond an electroformed nickel cap. Nickel is harder and more durable against high-speed impacts, but it's also heavier, so they keep it limited to where it's needed. In the worst conditions, these strips of metal act like the titanium skid plates of F1 cars. The blades impact the hard silica sand at immense speeds, creating 2 halos of hot metallic debris. The rotational speed of these 2 prop rotors need to match, particularly in hover, where unequal lift will quickly cause a crash. The problem was, the only way to reliably ensure that two engines operate at the same speed is to link them mechanically, and the path between them was a veritable mechanical obstacle course. Viewing head-on, you'll see the wings tilt up slightly, by just 3.5 degrees. This subtle dihedral angle gives the nacelles enough clearance to rotate into the parallel position. But the wings are also swept forward for no other reason than to give the prop rotors enough clearance that they don't shred the fuselage. On top of navigating these angles, this drivetrain had to deal with the nacelles rotating, the wings flexing, and the entire wing rotating parallel to the fuselage on a giant ring, all the while rotating 6,300 times a minute, and in the event of an emergency, be capable of transferring half the engine's torque to the other engine, so it could land less aggressively in an engine-out situation, with a final prayer that they could somehow not make this a nightmare to maintain. Remarkably, the V-22's engineers developed an innovative, lubrication-free coupling system, replacing the lubricated gear system of the XV-15. A flexible coupling that was stiff in torsion and could handle spinning at 6,300 RPM and do it even if the shafts moved 3.5 degrees out of alignment. This is called a multi-disc convoluted diaphragm flexible coupling. You can buy off-the-shelf versions yourself, but the V-22 was an extreme, early application of this technology that drove development. Each shaft has a stack of thin 0.2mm stainless steel diaphragms with spacers attached. Multiple thin discs offer more flexibility than a single thicker disc, like the leaf springs in a car. The convoluted part simply means the discs aren't flat, they have this wave pressed into them. Being lubricant-free and a simple disc made replacing them easy, which made the V-22 maintenance crew's life slightly less of a nightmare. But honestly, this part is remarkable in its simplicity. In 25 hours, this 0.2mm thin disc goes through 10 million revolutions and deals with being shoved, shook, and bent out of alignment over and over again. And thankfully, when a disc starts to fail, its squeaking is easy to hear. And even if one failed, the V-22 was good to keep flying for another 5 hours at maximum torque. To make things even more difficult, there are fuel tanks located here in the sponsons, and that fuel has to get to the engines, located all the way out here on the other side of a giant rotating coupling. Documents on how this worked are sparse, but from the clues I could piece together, I think this actually worked remarkably similar to this rotating house that appeared in a Tom Scott video. Essentially, you carve sealed grooves into a stationary ring and then cap that with a rotating cover. Our team actually animated this for Tom years ago. And you may have heard recently that Tom Scott has returned from his hiatus and is now releasing new episodes of his new series Tom Scott England early on Nebula every week, which you can sign up for with this QR code or the link in the description. Thankfully, this coupling didn't need to deal with high-pressure hydraulic fluid, as the auxiliary power unit, mid-wing gearbox, and hydraulic pump were all mounted inside the rotating wing. The V-22 is truly a mechanical wonder. The drivetrain packed into this rotating wing is bewilderingly complicated. The V-22's self-imposed tornado can cause havoc for the engine's compressors, but the engineers went to great lengths to minimize the pain and suffering of the maintenance crews once again, with some clever aerodynamics. As the air enters the engine inlet, it's forced to make a sharp turn. Clean air can follow the bend. Heavier grit and sand can't turn as easily, so it separates out and gets routed away. The engine output is geared down to between 412 RPM for vertical takeoff and 333 RPM in cruise. One prop rotor gearbox gets an extra gear to spin it in the opposite direction. This cancels out the adverse rolling moment that the huge gyroscopes mounted on each wing create. After the turbines, the airflow is pushed through a mixer that deliberately drags in cooler outside air and blends it with the hot exhaust before it exits. So instead of a tight, bright hot plume, the exhaust gets spread out and cooled down. And it's aimed outward away from the fuselage so the hot flow isn't blasting nearby structures or getting pulled back into other inlets. With all of these complicated mechanics, the Osprey has garnered a reputation for being unsafe. But what does the data say? Since 1991, there have been 25 incidents involving the V-22. 9 were caused by pilot error, 10 by mechanical failures, 2 were a mix of both, and 2 are still under investigation. This has led to the unfortunate death of 58 service members and has injured another 52. But how does this compare to 2 other helicopters, the Sikorsky H-60 and the Chinook H-47? Since its debut in 1979, the H-60 and its variants have had 390 incidents, resulting in 970 deaths. 60 of those deaths happened in the last decade, which is 2 more than the V-22 has caused over the past 30 years. The H-47 has historically had the Army's highest death rate per incident. Between 1966 and 2005, 238 lives were lost in 10 non-combat crashes. But in recent years, the H-47 Chinook has had a huge improvement in safety, with 47 incidents and no deaths between 2016 and 2020. Simply comparing the number of deaths does not take into account how many aircraft have been built and how much they fly. In accidents per airframe, the V-22 fares quite well with only 0.0625 incidents per airframe, compared to 0.75 and 0.11 for the H-60 and H-47. But if you look by how much flight time, the V-22 has more deaths per 100k hours. This data shows a couple of trends. Larger aircraft like the V-22 or H-47 tend to have higher death rates per incident because they carry more people, increasing the risk per crash compared to smaller aircraft like the H-60. Also, more complex aircraft usually see a spike in incidents early on as problems are identified and fixed, but these issues tend to decrease over time as the aircraft matures and systems are improved. These comparisons are not intended to put the V-22 above other military aircraft or dismiss its safety record. No aircraft is without flaws, and every accident is a stark reminder of the risks faced by service members. However, the data clearly shows that the V-22's safety record is not an outlier. This channel is all about breaking down how things work, and we've developed a new animation technique with Lumifield, whose industrial CT scanners allow us to create these volumetric models of anything we can fit inside, allowing us to explore every hidden nook and cranny of some of the most intricate devices ever conceived. We already have 2 episodes ready for you to enjoy, and they're available exclusively on Nebula, the Nokia 3310 and the first generation iPod. With the help of Nebula, we hired a new animator with a background in electronic engineering to take the technique we developed and help us make one of these videos every month. Next month, we'll be breaking down how charger bricks work and compare a $1 gas station charger to a top-of-the-line charger. A monthly subscription is usually $6, but with my link or the QR code on screen right now, you can get an entire year's membership for just $30. We are currently running the show as a pilot, so if you want to see more of it, you gotta sign up now. Or if you're sick of signing up to new subscription services like I am, we created a lifetime membership, if you would rather just pay it and forget it. All Nebula subscribers also get a 15% discount code in their account subscription page that you can use to purchase our XV3 t-shirt. In a time when creative work is getting harder and harder to find, Nebula helped me hire a young, talented animator and create a new series. That's what Nebula is about, supporting creative work made by humans.